Is any relationship between two sets of numbers. So you have any size set. It can be sets of just 5 or 6 numbers each, or it can be like infinite sets, like all of the real numbers. And a relation is just any way that numbers from one set connect to the numbers from another set. A coordinate system is made up of two number lines, one for x and one for y, and they are used to represent relations graphically, either by a bunch of ordered pairs that have been plotted, or a line or picture, graph. Ordered pairs show the relationship between two of the numbers in the relation, one x, one y, and they're listed with parentheses, one number and then the second number. The x-coordinate, which is the first number, is the domain or the input variable. It's the first one. The y-coordinate is the second number. It's the range or the output variable, and I'll go into more about that in a little while. The x-axis is a horizontal number line, right here, and the y-axis is vertical. One way to remember that is y has like a long tail, so y itself is kind of vertical, so the axis is also vertical. If we have an ordered pair, let's just say 3, 10. Okay, we go for the x first, so I go over to 3 on the x, that's here, and then I'm going to go up 10 on the y. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's the location of the point 310. Okay, so mappings are ways to visually represent relations so that you can see visually what's happening. You have domains and ranges. The domain is the x value. What that is, it's the input variable. It's the value that you can choose. And then the range is the y value, so it's the output variable. It's the value that is determined based on the one you chose before. So basically you put an x in and you get a y out. If you think about it, like if you're cooking, so you're baking a cake, the domain is all the ingredients you put in the bowl to mix up, and then the range is the cake that you get when it comes out. So that would depend on what did you put in the bowl, right? Did you put vanilla? Did you put chocolate? Did you put sprinkles? Did you put chocolate chips? So the kind of cake you get depends on what you put in the bowl. So hopefully that'll help make sense. Okay, there's a couple different ways to represent a mapping. You can do a set of ordered pairs. Okay, so I can just start listing any group of ordered pairs. You can make a table. So you have your x values and your y values. You can do a coordinate plane. So I'm just going to put random dots, but these would all represent points. Or you can do an actual mapping. With the mapping, you list all the domain elements or values in the first box. You list all the range elements in the second box. You never repeat. So if there were, let's say there was a 3, a 7, and another 3, I would only list it one time in each box. So only each number only goes once in a box. And then you draw an arrow between the numbers that go together. So 2 went with 3, so put an arrow. 5 goes with 7, -6 goes with 2. So we'll do the table first. So I can list X and Y. And I'm just going to list the X values. I have 2, I have -2, I have 5, I have -1. And then the Y's that go with them, 2 goes with 5, -2 goes with 3, 5 goes with -2, and -1 goes with -2. Make your coordinate plane 2, 5, so X is 2, Y is 5. And -2, 3, 5, -2, and -1, -2. So that's the graph. Oops. And then finally we have the mapping. So I put the domain and range. So my domain elements were my x's, right? So 2, -2, 5, and -1. And then my range, I had 5, 3, -2, and -2, but I don't list it twice. Okay. And then I draw arrows. 2 goes with 5, -2 goes with 3, 5 goes with -2, -1 goes with -2. Okay, so domain and range. The domain is all of the x values, so I have 2, -2, 5, and -1. And the range is all of the y values, so I have 5, 3, -2, and -2, so I only list that one time. Independent variable. That's the domain. Remember I said that's the one you can pick, that's the input. So it can either be chosen, for example, if we're making cake, what ingredients we use to put in the cake, that happens, right? That can be chosen. Or it can just happen in general. For example, time. Time passes. Time is an independent variable. We can't choose to not have time pass. You know, I can't just say, well, I've decided that I'm going to stop aging now and time is no longer going to pass for me. It doesn't happen that way. So independent variables, they are either chosen or sometimes like they just happen, like the passage of time. Then dependent variables are a result of the independent variable. So they depend on, so if you're talking about the cake, it depends on, you know, the kind of cake you end up with at the end depends on what you put in the bowl to start with, right? You wouldn't put carrots and cinnamon and raisins or whatever in a bowl of cake and expect to get chocolate cake out when you took it out of the oven, right? That you'd have to put chocolate in. So same thing with like time. How old I am depends on how much time has passed since I was born. So dependent variables actually require knowing what the independent variable was, what happened initially to give you the result. Does that make sense? Okay. So to identify them, sometimes it's easier to figure out what the dependent variable is, like if you're given a word problem situation. So it's easier to identify, okay, this depends on something else happening. So the thing that depends is the dependent variable, and then that other thing happening is the independent variable. Does that make sense? So here, if we look at this dance committee question. Okay, we've got, they're selling tickets to the fall ball. Okay, the more tickets they sell, the greater amount of money they can spend for decorations. So which one of those depends on the other? Any clue?
The selling the tickets for the ball would be independent. It doesn't change. They're selling the tickets.
They're going to sell the tickets, yeah. It's the decorations that depend on how many tickets they sell, right? So then the ticket sales, that's independent. And then the decoration money, that's dependent. Because you're right, they're going to sell the tickets anyway. You know, how many they sell and how much money they get, it determines how much decorations they can have. Okay, generally the average price of going to the movies has increased over time. Which one of those is dependent on the other?
Average price is independent, right? And then it's steadily increased is the dependent. Or
Close. The price increasing is the dependent. The thing that is independent that's going to happen no matter what, time. Anytime you see time as a possible variable, time is always independent. Time happens, right? Time passes, there's nothing we can do about it at all. Can't stop it, can't slow it down, can't reverse it. So it's independent to like the extreme. It's independent of us. If all of us cease to exist right this second, time would still happen. Doesn't care about us one way or the other, it just happens. So it's very independent. So a function is a special kind of relation. Okay, so remember, relation is relationships between two sets of numbers. And a function is a special kind of relation where every value of the domain, so every input or independent variable, every input only gives you one output or only one range. So what I have is, if I have a domain each domain element will only go to one range element. So on this side, you'd only have one arrow each. Each has a C in it. Otherwise, it's just eh. Okay, so each one of these only has one arrow because it only goes to one range value. Okay, another way to look at a function is pictorially. If I draw some curve, even or a straight line, do you see how each one of these x's only has one y? That's also a function. Okay. So you're looking just at the domain. And you count the arrows from each number. Okay, 1, 1, 1, 1. Okay, one arrow. If you have more than one arrow, okay. So you'll notice though I only looked at this side. 1, 1, 1, 1. So my answer to this is yes function. Okay, because I have 1, 1, 1, 1. Look at this 6. This 6 has 2. But I didn't say anything about the ranges, right? I said that the domain, each one in the domain can only go to one number. Technically speaking, I could have one element in the range and every single element in my domain could go to that same one. This is still a function because they each only have one arrow. Okay? To determine if it's not a function, if it has more than one arrow, so like if I do this. If 2 goes to 3, and 4 goes to 8, and 4 goes to 9, this right here, 2 arrows, tells me it's not a function because I have 2 arrows coming off of that 4. And that's not okay. So you only need to look at this side, the left. Another method, I'm going to do a sideways table so we have more room. If I have a table, I look at my x's, and do you see how these 2 repeat? I have 2 1s, and then I look at what they go to. If these 2 numbers here were the same, this would be okay. Because I'd say 1 goes to 4 and 1 goes to 4. Except it's not the same. It's negative 4. That means 1, my x value of 1 is going to 2 different y's. That's not okay, so that's not a function. Okay, so there's 2 kinds of functions. There's discrete and continuous. Okay, discrete functions are made up of individual points. They don't run together. Think about if you have a jar, and every day I put 5 marbles into the jar. So on day 1 I have 5 marbles, on day 2 I have 10 marbles, on day 3 I have 15 marbles. But those don't run together because it's not like between day 1 and day 2 the marbles are gradually growing into 10 marbles. It went from 5 marbles for the first day, and then when I threw 5 more in the next day, it's now 10 marbles. It didn't, like, do you see what I'm saying? Continuous functions are made up of many points that flow into one another. That's things like growing, or like, you know, if you drain a pool, it drains slowly over time. Or you grow slowly over time. Or you fill things up slowly over time, like with water. It flows. If you think about your growth, your height, you weren't 4 feet today, and then a week later, like you go to bed one night and you wake up and you're 4'6", or a year later, or however fast it happened. But it's not like you were 4 feet up until that next time you about to measure, and then suddenly overnight you just were instantly 6 more inches, boom, like that. You didn't just, right? You gradually increase your height over time. That's continuous. So if you graphed your height, you take the times that you actually measured your height, you plot those, and then you put a line between them, because between day 1 when you measured your height and day 2 when you measured your height, you grew. It wasn't just a quick jump. Does that make sense, the difference between the two? what we have is there's an ice sculpting contest, and each sculpture's height is measured because it has to be within the regulated height range of 0 to 6 feet. The measurements are as follow. Team 1 is 4 feet, Team 2 is 4.5 feet, Team 3 is 3.2 feet, Team 4's was 5.1 feet, and Team 5 was 4.8 feet. And then we're going to do these A, B, C, and D, and we're going to do them over here. So A says we're going to make a table showing the relationships between the teams and the heights. And I'm going to call the team numbers X, and I'm going to call the heights Y. So Team 1's was 4 feet, Team 2's is 4.5 feet, Team 3 is 3.2 feet, Team 4 is 5.1 feet, and Team 5's was 4.8 feet. Okay, so that's my table. B is asking me to determine the domain and the range. These is my domain, right? All my X values. This is my range, all my Y values. Okay, so that's B. C asks us to write the data as a set of ordered pairs. Now, when you're actually making a graph, you can just look at this and go, okay, that's an ordered pair. You don't actually have to write them, but I'm going to do it just for now. So 1, 4, that's one ordered pair. 2, 4.5, that's that ordered pair. 3, 3.2, that's this one. 4, 5.1, and 5, 4.8. And then graph the data. So now we're going to graph it. Before I graph, I always look at what kind of numbers I have. My numbers are all positive. So I don't need a lot of space for negatives on here. That's a bit thick. So what I'm going to do is I'm going to put my axes kind of low and to the left because I have all positive numbers, and positives are up here in this corner. And then what I'm going to do is I'm going to go by 2s to give me room to put the decimals in. Okay. And now I'm going to graph. So Team 1's was 4 feet. That's right here. Team 2 is 4.5 feet. So that's right here. Team 3 is 3.2 feet. So 3 is right here. So 0.2 is just above that somewhere. Team 4 is 5.1 feet. So here's 5. 0.1 is just like right on top of 5. And then Team 5 is 4.8, which is just right below 5. Okay. Now for D, we're supposed to state whether this is a continuous or discrete function. What do you think? Should these be connected with like some sort of a line or curve, or are these like individual points? Yeah, they're individual, right? Because each team made their own sculpture. It's not like the sculptures bleed into each other. So this is discrete. And discrete is because it's individual. Does that make sense? Okay, so the weight depends on how many quarts are in there. So that's X, and then the Y is the number of pounds. So we'll list that. Those are our tables. This is my domain. This is my range. if we put this as a set of ordered pairs, that's not right. Don't write that. Okay, that's correct. And then this one's not right. Left off my x's. Okay, so again, I have all positives. So I want my axes to give me room on the positives. So I'm going to put them, further left and further down. I need at least 13 spaces here, so this is 15 total now, so I'm going to just do each one of these as one. But I can space this side out because I only have to go 0, 1, 2, and 3, so I might just, go out 3. Make this 1, 2, and 3. Okay, at 0 ounces of birdseed, or quarts, I'm sorry, quarts of birdseed, it's 2.3 pounds. So here's 2, 0.3 is going to be somewhere in between there. When we have 1 quart, we weigh 6 pounds, so that's right here. When we have 2 quarts, we weigh 9.7, so that's almost 10. And then we have 3 quarts, we weigh 13.4, so that's halfway between 13 and 14. Now, to determine if this is a discrete or continuous function, you have to decide the weight. Do birds come and in one gulp, like, take a whole quart of seed and just swallow it? No, right? Like, birds eat little bits at a time, and so the weight is going to gradually decrease as they're eating it, and then it'll gradually increase as you pour seed in, right? So that means it's going to be continuous. And if it's a continuous function, we connect it with a line or a curve. Because the weight is going to fluctuate in between here all over the place. Does that make sense? Okay, so the vertical line determines if a graph is a function. So if you have a vertical line, say like this one, and I put it over top of the graph, it can only touch the graph one time at any point. And as you can see, as I move this across, it's only touching the graph in one place at a time, right? Okay, so this graph passes the vertical line test, so it is a function. Okay. If I come up here with this vertical line, oh, look at that. It's touching here and here. So it's touching the graph more than once. So it failed. So it's not a function. Okay. Because it's touching twice. Now, this next one is a little bit tricky, because as you come across, you're doing okay, but then as soon as you hit right here, it looks like you have an issue. But you don't really have an issue, because you see how this is closed and this is open? This open dot means that it doesn't really exist right there. So it's still only touching in one place. This open dot doesn't actually exist. So it is a function. And that's the only time that it can touch the graph in two places and still be a function, if one of them's solid and one of them's open, or they could both be open, but at least one of them has to be open, because that means that point doesn't exist. Not really. So is a function or not, we can make a list of tables, or sorry, a table of values, and then we can graph the equation. So let's just say I do y equals, not plus 3. Let's change that. We'll do minus 3. Y equals 2x minus 3. Pick any x you want. I like to pick 0. 0 is nice because 0 makes x go away. Right? So 2 times 0 is 0. It's gone. So y is going to be negative 3 because it's 2 times 0 minus 3.
That's a multiplicative property of 0.
Mm-hmm. Yeah, multiplicative. Okay, if I pick 1, that means y equals 2 times 1 minus 3. So that's 2 times 1, which is 2, minus 3 is negative 1. If I pick 2, I have 2 times 2 minus 3, so I get 4 minus 3, so that's positive 1. You want to do about 3 points to make sure you have a straight line. We could do a 4th one just to, so let's go negative 1 just to see what happens. If I do 2 times negative 1, that's negative 2 minus 3 is negative 5. Okay. So let's go here. We have 0, negative 3. That's this point. I have 1, negative 1. I have 2, positive 1. If I go to negative 1, I have negative 5, but I run out of space, so I can't actually graph this on this one, which is fine. If you look here, this looks like a pretty straight line, doesn't it? So we graph our line. And then we're going to make a vertical line for a vertical line test. And what you can do is you can take your pencil and just run it across your graph. Your pencil's vertical. And as long as your vertical line is not touching the graph more than one place at any time, you're fine. It's a function. Function notation, okay? If you see function notation, it does indicate a function, so you never have to test it. And in function notation, f of x replaces y. But they're the same thing. So they're both range. Okay. And the whole point of function notation is because of this right here, this f of 2. Whatever number No, I knew you guys all have me for 2 terms. So what we do is if f of x is 4x minus 7, okay? So I'm just going to rewrite it. Negative 4x plus 7. And I want to know what f of 2 is. I'm going to replace x with 2. And then I'm going to go from there. Negative 4 times 2 is negative 8, plus 7, that's negative 1. Okay. Now if we come here, we've got 2 things going on. We have f of negative 3, and then we have this plus 1 situation. Okay. When this happens, you take whatever you get from plugging in the negative 3. So what you do is you take the f of negative 3 first, and then we're going to add 1 to that because of this plus 1 right here. Okay, so first I'm going to do the f of -3. Okay, so I put the -3 in where the x was. So that gives me 12 plus 7, which is 19, right? Well, f of -3 plus 1, that's this f of -3, which was 19, right? Plus 1. Now you don't have to do it separately like I just did. I just wanted to make sure you guys understood the process. What I would normally do is I would take the f of x, plug in the -3, and then this plus 1, I just add it to the end. Does that make sense? And I'd still get the same answer. So if it makes sense to you to do it separately, you can do it separately. Or if it makes sense to you to go ahead and put it together, you can put it together. Yeah, right? Except here, instead of h of t, I want to try to find h of 4. So everywhere there's a t, I'm going to plug in a 4. Okay. Okay, so I get the 16 from the 16 squared, or 4 squared, and then 68 times 4 is 272. This is -256 plus 274, if I add those two together. So this is positive 18. Okay. So again, I just took this 4 and I plugged it in wherever there was a t. Now this one's a little different. I'm going to rewrite this again. Now h of g is the same idea. Everywhere there's a t, I'm going to replace it with a g. Okay, so h of g is not too bad. But they want to know what this is. So they want to know 2 times h of g. So it's going to be 2 times everything that h of g was. So I'm going to have -32g squared plus 136g plus 4.